In less than 30 years, scientists' description of the ocean has completely changed.
We realized that the ocean was filled with whirlpools. It was a turbulent fluid with no current running straight. It revolutionized the way we saw the ocean.
In fact, the currents determine the geography of life in the oceans. A burning question today is, what impact will melting ice fields, and therefore a change in the quantity of fresh water, have on the deep thermohaline circulation?
The ocean plays a vital role in exchanges with the atmosphere, particularly the absorption of carbon dioxide. So the ocean plays a key role in global climate.
The ocean is the most important part of our global climate system, and that's why the research is so intense right now.
To understand what happens in the oceans, we'd need to be able to monitor a drop of water through the heart of the oceanic machine and try to decipher the processes that occur.
For a long time, the sea remained a relatively obscure world. A large fish tank that we'd cross without worrying too much about its internal functioning, and even less about its role in the existence of life. At the end of the 1980s, we knew more about space than about the oceans, which nonetheless cover a cool 70% of our planet. A planet which was showing worrying signs of warming up. Analyzing the mechanisms at work in this upheaval became a matter of urgency. So the scientific community turned to the oceans.
Today, we realize that the ocean is a very complex machinery with several engines, multiple gears, and we can see that everything is connected. That this global system connects all the planet's waters and all its basins. Everything is linked and interconnected.
Bruno Blanc is one of the oceanographers who wondered about the movements of water masses, about their journeys all around the world. He sensed there might be a trail to be followed that would reveal the secrets of the ocean machine.
In fact, to properly understand what happens in the oceans, you'd have to take a single drop of water and be able to follow its sea journey. It might fall, for instance, into the ocean, in one of the branches of the Gulf Stream off Ireland, and we'd follow it to the center of the ocean machine and use it to decipher the mechanisms that occur.
This idea isn't just a dream. Bruno Blanc has in fact modeled the path of a drop of water carried by the sea currents. The result confirmed the researcher's intuition. The water droplet will transit through all the oceans on the planet before returning several centuries later to its starting point. A huge circuit which passes through the most remarkable phenomena the oceans have to offer, all of which are now the subject of scientists' research. We will tell the story of that voyage.
The drop of water heads north, carried by a succession of surface currents which cool in contact with the atmosphere. Cold water, which is denser, will tend to sink into the ocean, and when it arrives in the polar seas, other processes will contribute to making it dive deeper.
The voyage leads without further ado to the heart of a phenomenon which influences global climate in its entirety. This happens in the cold season under the ice flow. The ice, formed by the freezing seawater throughout the winter, expels via gravitation the salt it contains. This produces a heavy, cold brine, which sinks to the depths, dragging with it huge quantities of water at more than 10 times the flow rate of all the rivers in the world. This gigantic undersea waterfall acts just like an engine. 2,000 meters further down, it generates a wide conveyor belt of salty, cold water which spreads southwards. This migration is offset on the surface by warmer waters which are pulled northwards. Thus, the thermohaline circulation is created, thermo for temperature and haline for salinity. A vast circuit of currents responsible for transporting heat and therefore for the climatic balance of the planet. In short, our thermostat. And it's this Arctic engine, indispensable to temperature regulation, which is now worrying the scientists. For the last 20 years or so, Louis Fortier has carried out a good many field missions, attracting the attention of policymakers to the ongoing transformations in the polar environment.
The Arctic Ocean is a very small ocean, accounting for barely 4% of all the ocean's surface area. But it has a role disproportionate to its size because it hugely influences the currents of the North Atlantic and indeed the whole Northern Hemisphere. But over the last few decades, the major discoveries in the Arctic are obviously the rapid disappearance of the polar ice cap, as well as the acceleration in the Greenland glaciers melting. So right now, with the ice flow melting, the surface waters reaching the Greenland Sea and the Labrador Sea are less and less salty and will be less and less dense when the ice fields form. We fear this will result in a gradual slowing of the deep water thermohaline circulation.
Can fresh water really hinder the workings of the Arctic engine? And what consequences would that have for the climate? In actual fact, the phenomenon did occur some 13,000 years ago at the end of the last ice age. Then the Arctic Ocean was a huge, immobile block of ice, frozen stiff by the intense cold. Nothing moved until the atmosphere warmed again. In a few hundred years, the landscape was totally altered. Glaciers melted, the ice fields disintegrated, making way for currents which dragged icebergs in their wake. The Arctic Ocean began to function more or less as it does today. But at the same time, it found itself confronted by massive quantities of fresh water from the melting flows. So what happened? The answer is found in these core tubes of sediment sampled from the bottom of the ocean. They're made up of various strata of materials deposited by currents and drifting ice over time.
Here we begin to see deglaciation with intervals marked by sediment, which is far lighter, a light brown. Here, if I had to date the interval between this and that, I'd say that around here we're at 11,000 to 12,000 years before the present day.
Claude Hilaire-Marcel has made a speciality out of reading and interpreting these mysterious sedimentary cryptograms. Here he gleans a possible pointer to the disruption threatening the planet.
The sediment here is essentially coarse grains. It's therefore probable, as they're several millimeters in diameter, that it's the kind of material usually carried by floating ice or icebergs. This gives a picture of an ocean in which the sea ice has begun to move around again, and the melted water from this sea ice will penetrate the northern seas, in other words, the Norwegian Sea, the Greenland Sea, and then towards the basins of the North Atlantic, and will lessen the salinity of those basins and slow the formation of deep water in the North Atlantic.
When the flow rate of the great undersea waterfall slows, the oceanic conveyor belt weakens. Less cold water is sent to the depth. Less warm water is pulled northwards to the surface. The thermostat goes wrong.
We'll suddenly have a huge cold snap in the North Atlantic. So for around 1,000 years, almost Ice Age conditions will set in. The ice front in the North Atlantic will shift around 1,500 kilometers south following this episode, which is entirely caused by the Arctic. The consequence of this kind of observation is a realization that if, in the future, a lot of fresh water arrives in the Arctic, it can significantly disturb the overall oceanic circulation.
So now we're heading south. Our water droplet will cross the Atlantic Ocean from north to south, following a deep water current at a depth of around 2,000 meters on the western side of the Atlantic Basin, a current that results from the formation of dense water in the Arctic Ocean. Once we get to the southern hemisphere, we come to a strategic place for the global climate, the Southern Ocean. An ocean whose importance has long been underestimated because it's hard to access and therefore poorly measured. In fact, it's a particularly inhospitable region.
The Southern Ocean, a vast mass of tumultuous waters encircling the Antarctic continent. Located at the far reaches of the world, it's the least accessible and the most dangerous of all the planet's oceans. A challenge for whoever would explore it and understand the way it works. Here there is no land to slow the world's most violent winds in their unceasing round. Nothing either to reduce the strength of the circumpolar current, a monster which whips the waters into a dizzying ride around the Antarctic continent. It's the most powerful current on the planet, in places 2,000 kilometers wide, capable of reaching as far down as 4,000 meters in depth. But through a lack of observations and data in situ, the Southern Ocean and its terrible current have long been sidelined in the models built by the scientists. Sabrina Spesch is a researcher who sensed an urgent need to know more about this ocean with the bad reputation. In 2004, she organized one of the first large-scale programs devoted to studying Antarctic waters.
In the 1990s, we realized that this ocean was supplying waters that were very important to the global oceanic circulation. And as these campaigns were very rare, we needed to understand a lot more. In this type of campaign, the aim is to measure the variables which give an identity to what is called a water mass. In other words, the temperature, the salinity, the pressure in terms of physics, and chemical elements like oxygen, to obtain time series that show us both how we can recreate the movements of water masses in this region, and therefore understand the exchanges to the south of Africa between the various oceanic basins, and also how these waters can change with time. There's the notion of variability. Like the weather varies in the atmosphere, the circulation can vary from one year to the next in the ocean.
Thanks partly to campaigns led by Sabrina Spesch, scientists have managed to identify the route taken by the massive volumes of water which circulate around the Antarctic continent. We have thus discovered the way in which the three great oceans on the planet are connected. In fact, everything revolves around the circumpolar current, which acts as a transmission belt. In its ceaseless round, it captures the deep, cold waters from the three major oceanic basins, that is, the Atlantic, the Pacific, and the Indian. It slowly brings these waters towards the surface and redistributes them from one ocean to the other.
The results of campaigns are not yet all analysed, but what we can say today is that this global oceanic circulation is important for heat exchanges, for example, between different oceanic basins, and in interaction with the atmosphere, particularly in the absorption of carbon dioxide. So the ocean plays a key role in the global climate.
But the discoveries didn't stop there. Other observations which magnified the role of the Southern Ocean today force scientists to reconsider the models.
What we can see here, along the Antarctic continent, close to the continental slope and shelf, is the formation of bottom waters. The bottom of the ocean is carpeted by these waters, the densest waters we find anywhere in the oceanic basin, and which form in a very localized way around this continent. Only now are we beginning to notice them. We've made some observations, but we've no idea of the quantity of these waters that are formed. And the process seems to be linked to the polynyas that exist around the Antarctic.
Polynyas are huge stretches of water that are free from ice despite the extreme climatic conditions. In the Antarctic, polynyas are formed by very violent winds called katabatic winds, which jostle and fracture the ice flow, clearing vast zones of free water. These zones then become ice factories, where the ice field regularly forms and then disintegrates. On each of these cycles, it expels the salt it contains in the form of a cold, heavy brine, which sinks to the bottom. In what quantity and in which directions? These are the questions. David Barber is one of the first to address the phenomenon of polynyas. In order to precisely measure their characteristics, he chose to create them artificially. They called these ponds polynyas.
So people were always interested in these things, so they came up with a special term called a polynya. And so these puddles of open water in a place where there should be sea ice were always quite interesting to early mariners and to people that were, hunting seals or whales or whatever. And so polynyas have become something that have been very important in studying both poles of the planet when you think about climate change and how climate change is affecting things. And the reason for that is that this open water behaves much different physically than the sea ice around it. And so to study polynyas, you can do one of two things. You can go to the Arctic or the Antarctic where these polynyas exist, and we do that as part of our field programs. But what we've done here at the University of Manitoba is to build our own polynya. These polynya, they form deep water throughout the year. So even in the middle of winter when it's 40 below zero, and even here at the surf facility, that ice is causing the ocean water underneath to sink towards the bottom of the pool. And we're actually measuring that continuously as we're doing our experiments here at SURF. It's really the driver of how this ocean circulation works. And the polynyas of the planet play a very important role in this overall concept of deep water formation and the oceanic conveyor belt. Now, there are many, many polynyas in the Antarctic. They basically occur all the way around the Antarctic. They'll change in size from, tens of meters to hundreds of meters to thousands of meters. And then, practically speaking, they're in the thousands of kilometer size square area. Some of them can get to be very big, several 100,000 kilometers in size.
The measurements carried out in the laboratory, coupled with field observations, indicate that at the bottom of the Southern Ocean is a gigantic network of cold water rivers. Recently, the flow rate of one was successfully measured. It's equivalent to 60 times that of the Amazon. Thus, these discoveries prove the existence at the South Pole of a second real engine that is involved, as the one at the North Pole, in the global oceanic circulation. Two systems connected in a great conveyor belt that moves a whole network of currents around the world.
The ocean is the most important part of our global climate system, and it's the poles that are the engine of our global climate system because of the influence they have on ocean circulation and how this packet moves around the planet when you think of packets of water that are moving around the planet.
The more we discover about the currents and their effects, the more we feel a need to know more. In other words, to observe them more perceptively, more fully, on a permanent basis. But how, technically, can we monitor a world so vast? What tools can we use? One of the most ambitious solutions is to use little submarines stuffed with sensors, a veritable army of spies which constantly monitor temperature and salinity from the surface to a depth of 2,000 meters. Before being sent on a mission, these little robots are trained here, under the attentive eye of the engineers in charge of the program. To Loïc Petit de la Villéon and Nathanaël Le Breton, the world's oceans have become a vast playground.
There's an amazing revolution with this type of Argus program. Before, we'd go off to observe a phenomenon, something very precise. The boat would put to sea for a month or however long, but naturally we wouldn't be back until a month or a year after. Here, what we said was we wanted a program to observe the ocean which was large-scale, global, perennial and permanent. The target was to have 3,000 floats out at sea permanently. On this screen, we can see the movements of the network. At first, we kept things simple, and then gradually, as the easy parts were being covered, we headed south, and we'll see how things evolved. Here, typically, we find a ship on a long passage that has sailed all the way down that route. Now we can see that we're heading for the south a little more. The north is fine. The southern hemisphere was done a little later. So we can see that in the extreme south, there are still a few gaps.
The Argos system data, available free all over the world, are used in particular for feeding mathematical models. The challenge is to reproduce the dynamic of the oceans at any spot on the globe. But the problem is, in some zones, these little spies can sometimes be muzzled by the environment itself.
Here, our drop of water is journeying under the ice, which is not a problem to the droplet, because of course marine currents do exist under the zone which in winter is covered by sea ice. However, this ice is a major obstacle and unfortunate for the oceanic instruments, the profiling floats, which are supposed to surface periodically and transmit their data to scientists. To combat this, researchers have seized upon another measuring vehicle, which is not scared to go swimming under zones covered in sea ice.
Est-ce qu'il relâche ses nageoires? Ouais. Bon, ben là, je pense qu'il dort. Vous pouvez commencer à dormir.
The thing is, these sea elephants are amazing divers. We've put dive sensors on these animals that show they're capable of diving to a depth of beyond 1,500 meters.
We used a new generation of Argos beacons, which enabled us, on the one hand, to follow these animals as they moved around at sea, but also to study, throughout their journey, the diving behavior of sea elephants, and, when they dived, to measure the temperature and the salinity of the water masses crossed by the sea elephants, and therefore to characterize, from the oceanographer's point of view, the habitats and zones where sea elephants concentrate their fishing activities.
To reach these hunting grounds, this sea elephant heads south and prepares to explore waters covered with ice. The information gleaned by our special envoy means that for the first time, the oceanographic conditions associated with the formation of the ice flow can be recorded. And this rounds out the data needed by scientists for their models.
After several laps around the Antarctic continent, our water droplet feels like escaping from the circumpolar current. Of course, there are several possible exit gates, but one of the main ones, intensity-wise, is towards the Pacific. As you approach the South American continent, the waters branch off to the north and follow the coastline. First Chile, then Peru. That's the Humboldt Current. And this Humboldt Current allows us to tackle a key phenomenon in the circulation of water masses.
But what do these waters of the Humboldt Current hide for oceanographers, climatologists, biologists, and even a few geneticists to be spreading their nets here? For scientists on the Tara expedition, involved in a huge campaign covering all the seas on the planet, there are treasures to be found here. The subject of their research lives in these waters, and in astronomical quantities. This greenish soup is in fact teeming with life. It contains the very origin of our existence, but also that which enables us to live and to breathe on the Earth: plankton.
Plankton is very interesting for lots of reasons. First, it's our oxygen-producing machine. 50% of the oxygen that we breathe is produced by plankton. There are also organisms which hold carbon dioxide. In fact, 50% of the carbon dioxide that is discharged into the atmosphere is swallowed up by plankton at the bottom of the oceans.
The term plankton covers thousands of different species, in fact, both plant and animal, but which all have one characteristic in common. Their existence is entirely conditioned by the marine currents through which they grow and migrate. On the Peruvian coast, in particular, the exceptional abundance of plankton is due to the upward surge of deep, cold water, very rich in the nutrients needed for its growth. This vertical current of waters, called an upwelling, is generated by the winds which here regularly blow from east to west. It pushes the surface waters, which are warmer, out to sea, and forces the colder bottom waters to rise up towards the coast. Here, the upwelling is directly responsible for an amazing abundance of life in all its forms.
Another important thing about plankton is that it's obviously the base of the food chain. The unicellular algae are eaten by zooplankton, which are eaten by the fish, by the whales. So whenever there's a lot of plankton, like at upwellings, there's a lot of life, lots of fish, and so there's lots of fishing.
Among all the species of fish which benefit from the ecosystem, the anchovy is clearly dominant. Their proliferation makes this region the leading fishing grounds in the world, volume-wise. It represents less than 1% of the world's surface, but supplies 20% of catches on a global scale. But man isn't the only predator to benefit from this manna. Others, like sea lions and great birds, are keen to join the feast. Thus, this vast system, both economic and ecological, has been built around the movement of the waters. The ocean currents here generate not only the food chain upon which men and animals depend, they also give it its instability. And among all this disturbance, the most feared, the most spectacular, is called El Niño. This phenomenon occurs irregularly 2 or 3 times every 10 years. It all begins with a change in the wind patterns. The trade winds, which caused the upwelling, slow down and even reverse. This results in the cold waters that would rise up towards the coast being replaced by warm currents returning from the open sea. All this triggers a wave of atmospheric disturbance which mainly affects the tropical zones. Rainstorms and cyclones move towards the American continent. Meanwhile, Indonesia and Australia are hit by scorching droughts. But in Peru, the consequences are also economic and force scientists to increase their vigilance, the better to anticipate the impending disaster.
We know that the Humboldt ecosystem is characterized by cold waters. The surface temperature of the seawater is between 13 and 20 degrees Celsius.
A change in water temperature, a drop in the production of plankton, the entire ecosystem in Peru is turned upside down.
Naturally, this affects the species which feed on the phytoplankton and zooplankton, particularly the Peruvian anchovy. This affects not only its feeding process, but also the anchovy itself, which is used to living in temperatures of 15 or 16 degrees Celsius. And when the El Niño phenomenon comes to the northern zone of Peru, temperatures reach between 25 and 28 degrees Celsius.
Under pressure from El Niño, the anchovy is disappearing, and with it 99% of all industrial fishing. This has huge consequences for the country's economy. Today in Peru, they have learned to better predict the phenomenon and its intensity, and therefore to manage the stocks of fish accordingly. But beyond the local context, El Niño speaks volumes about the power of the link that unites ocean and atmosphere. Such gigantic climate disturbances around the world can be caused by a simple variation of the currents at one point on the globe.
Now our water droplet sets out on a very long journey, mainly on the surface layers, in other words, the first 200 or 300 meters of the column of water. It is pushed by the trade winds, so it leaves the American coast and is carried from east to west to Oceania by the southern equatorial current. As soon as it gets to the western edge of the Pacific, our drop of water is captured by the equatorial undercurrent, which sends it back towards America. It's a unique current because it flows at a depth of 100 meters, centered on the equator, and it flows in the opposite direction to the surface currents and winds. So this droplet will be capable of shuttling back and forth several times between the west and the east of the Pacific, alternately taking the surface currents and the equatorial undercurrent. This type of recirculation isn't uncommon. In fact, in every sub-basin there are internal circulation cells, which are of course added to the links with other basins.
A great merry-go-round which irrigates the oceans with its vital substance, plankton. For this reason, scientists are now seeking a better understanding of the effect of currents on all the microorganisms that enable the planet to breathe and to feed itself. But how to visualize this interaction? how to connect the circulation of waters and the biological diversity of the oceans. This challenge was taken up by Mick Follows at the Massachusetts Institute of Technology, MIT, by modeling the behavior of various species of plankton according to their environment. To do this, the researcher reproduced the physiological characteristics of these microorganisms and introduced them into a global model of the ocean.
Okay.
Thus, Mick Follows managed to create a virtual world in which the various communities of plankton live and grow in color, according to the currents and the variations in temperature and salinity, just as things happen invisibly in reality.
So this movie shows you something that we can't yet measure efficiently in the ocean, or we probably can, but we haven't done yet, which is the diversity of the phytoplankton. It's been measured at some local spots, but in the model we can ask how many different species are coexisting at any point in time and space. And so this is a pattern of the biodiversity, and we can find that places like the Kuroshio extension here are very high diversity. There are lots of different types of phytoplankton living there concurrently, and that's because of the confluence of currents, the motion of currents, and also the vigorous supply of nutrient resources that happens to coincide in these places. And so this gives you some idea of how the biomes of the ocean. So if you think about looking at the land, and you'll see going from tropical plants to savannas to fir trees on the mountains. This is kind of the analogy for the phytoplankton in the ocean. You're seeing the different biomes as you move around in the ocean and how they vary with space and time.
These images of marine life subjected to the interplay of currents are the fruit of the most advanced modeling that exists today. A virtual universe still under construction, which for Mick Follows will eventually enable us to test the various scenarios linked to climate change.
And we can start to interrogate models like this to understand why those boundaries are moving, how they might change if a permanent change in the physics of the ocean, for example, a warming, shifted those intersections around.
Our drop of water still carries westwards, pushed by the surface equatorial current. Once past Madagascar, the current separates into two branches. The northern branch leads to recirculation in the Indian Basin. But to go towards the Atlantic, the southern branch is more effective and quicker, and our droplet will take the Aguilas current, which is the counterpart to the Gulf Stream for the Indian Ocean. And that current will lead to the southernmost tip of Africa.
By penetrating the coastal waters of South Africa, the droplet may well come up against the most spectacular migration of sardines observable on our planet. The phenomenon is linked to the presence of a powerful upwelling. Here, the cold waters from the Southern Ocean are flowing up along the coasts. They form a corridor of water rich in plankton, ritually taken by millions of sardines every year, to the delight of a whole army of predators. Though it may escape the shoals of sardines, the droplet cannot avoid the strange eddies of the Agulhas current.
It's moving around a lot. Our droplet of water is captured by an oceanic whirlpool. This is another phenomenon that has long fascinated scientists, but today we're realizing their importance to the climate and to ecosystems.
A whirlpool, but how do you spot them? How do you see them? In reality, such a structure is undetectable from the Earth. Even when you get up high in a plane, more often than not it will remain invisible. And yet the vortex is there, somewhere, loaded with a considerable energy, capable of dragging millions of cubic meters of water with it. To determine its existence, you have to go much higher. Only satellites are capable of spotting and monitoring the movements of these strange oceanic vortices. In particular, thanks to the onboard systems that measure the relief of the oceans and can detect deformations generated at the surface by whirlpools. For Marina Levy, who studies these structures and their effects on the marine environment, the satellite revealed the scope of a long unsuspected phenomenon.
Before, there were boats which knew very well that there were whirlpools, and so they had identified what they called coherent vortices, or in particular Gulf Stream rings. But it was really with height-finding radar that we realized that the ocean was filled with whirlpools. It was a turbulent fluid, with none of its currents running straight. It revolutionized our way of looking at the ocean. There are thousands of whirlpools in the ocean, and all these whirlpools interact with other whirlpools. Some can survive a long time, up to 2 or 3 years, but they take a few weeks or a few months to form. They're also highly energetic and associated with high speeds, in both horizontal currents and vertical currents. In fact, they generate movements of water from the bottom of the ocean to the surface, and vice versa, which are very rapid. The fastest vertical movements of water you can have, around 20, 30 meters sometimes up to 50 or 100 meters per day.
Essentially, the whirlpools form at the crossroads of marine currents. To the south of Africa, the clash between the circumpolar current and the Agulhas current is so violent that it produces whirlpools capable of crossing the Atlantic in a few months, taking with them our drop of water. But above all, this turbulence produces intense mixing, whose effects on the physical and chemical properties of the ocean we're now discovering.
These whirlpools are all about speed, horizontal and vertical, and they carry heat. And as heat transporters, they're important to the climate. In addition, these whirlpools play a part in the ocean's carbon capture process.
By shaking up the waters vertically, the whirlpools activate the production of plankton, a major carbon consumer. At the same time, they drag towards the depths waters in which carbon dioxide from the atmosphere is already diluted. Thus, this long-ignored turbulence is revealed to have a real impact on the climate machine.
So today, we're busy trying to understand what, quantitatively speaking, is the role of these whirlpools on the carbon cycle. It's clear that today they cannot be overlooked in our carbon assessments.
The planet is getting warmer, suffocated by the carbon dioxide emitted by man's activity. But the ocean is there, and it dissolves close to 50% by absorbing the carbon it contains. Until now, this process has slowed down the climate's worrying evolution. But how long can that go on? What is the ocean's carbon absorption capacity? It's that particular question that the scientific community is now trying to answer. The thing is, carbon exchanges between the ocean and the atmosphere are very complex to quantify, and they work in both ways.
It's an important, urgent matter to evaluate this absorption of carbon by the ocean. We recently realized that carbon was absorbed chiefly at whirlpool level, poorly sampled by current oceanographic campaigns. Otherwise, it's where deep waters or bottom waters form, which means mainly in regions of the North Atlantic and in the Southern Ocean. But at the same time, the carbon-loaded deep waters that come from the North Atlantic rise to the surface to the south of the circumpolar current and restore that carbon to the atmosphere. And this makes precise evaluation difficult of what carbon is entering the ocean compared to what is leaving.
It's difficult today to establish a global assessment of carbon absorption. However, the results of the most recent studies are rather pessimistic. They reveal that locally the quantity of carbon absorbed is tending to decrease. The North Atlantic, for example, absorbs only half what it did 10 years ago. In the Southern Ocean, it's 10 times less. At the same time, the concentration of carbon dioxide in the ocean has greatly increased. Scientists have calculated that by the year 2100 it will triple for the first time in 20 million years. The effect of all this is to gradually increase the acidity of the water and threaten the growth of shellfish and coral organisms.
The global ocean has until now played an extremely important role in reabsorbing and holding our excess carbon dioxide from the atmosphere. And it's like a reservoir filling up. Not only will it soon stop recapturing this carbon dioxide, but because its chemistry is changing, because it's acidifying and warming, this reservoir will start to reject the CO2 it has been storing since the beginning of the industrial age and return it to the atmosphere. And that is worrying, because very suddenly we may see concentrations of CO2 in the atmosphere increase by 50% or even double, and global warming will accelerate.
When it comes within range of the South American coasts, the whirlpool has lost most of its energy. It disintegrates and releases its content. So the drop of water is no longer captive, we see it cross the equator, and it is retrieved by the main circulation cellule in the North Atlantic.
The Droplets Round the World tour will have taken close to 650 years. However, in line with our new vision of the oceans, we will now have to take a very careful look at the path it takes and watch it follow all the twists and turns of the Gulf Stream, recently rebaptized the Lord of the Rings by the scientists themselves.
By reviewing this trajectory, we realize that our drop of water has felt movements at very different scales throughout its journey. We've seen the scale of the oceanic basin with its circulation cell over the North Atlantic. There's also the very large scale, with our droplet toppling over from one ocean to another. And then there's the small scale, with the droplet caught up in a whirlpool. So the ocean dynamic is a complex puzzle, which is made up of pieces that are very different in size, yet they fit together, complement one another, and interact. So the ideal thing for us today would be for us to represent this whole dynamic digitally, just one model incorporating every scale at once.
Even though there's still a long way to go to complete the great virtual model of the oceans, the scientists' work is already showing significant results. And it's forcing us to take a different look at the world which washes our coastlines. It's hard not to see beyond the apparent calmness of these waters the very complex mechanism which underpins our planet's fitness for habitation. It's hard, too, to doubt the changes threatening the whole system and revealing its fragility. it has never been as clear that our existence, past and future, is intimately linked to the movements which drive the oceans at their very heart.
Our droplet is going back to its beginnings. We see it come back to where it started from. Of course, whether in the real ocean or in this digital model, the number of possible trajectories is unlimited. Nonetheless, the oceanic circulation is most definitely a huge circuit. And in fact, perhaps our droplet has started off on its second lap.